This is lesson 3-3, comparing linear and nonlinear functions. It starts on page 178 in your workbook. I want to start by looking at this essential question. And this is about how can you compare two functions? And there's really two things that I want you looking at. I want you looking at the slope. Sometimes the book is going to call it the rate of change. And I want you to look at the y-intercept. That is our starting point. And so this lesson is all about which one grows faster, which one started at the higher rate, those kinds of questions. So here we are on page number 178, and we are going to compare two linear functions. An auto assembly factory needs to purchase new welding robots. The factory manager has information on two different models of welding robots. The welding rates for each model are shown below. How do the welding rates for the two robots compare? Okay, so we went ahead and took the orange robot's data and we made it a little bit bigger. It's right here. Nice table. Now before, when we were figuring out slope, we were always going this way. Divide, 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 divide. Today I want to introduce the fact that you can also, let me change colors here, you can also go this way and find your change in y over your change in x. So you figure out how much your y changes over how much does your x change. How much does your y change over how much does your x change? So they did that and they figured out that our rate of change, or the slope, is 10 4/10 every time we did that. Over here, we have a lovely graph. And remember, we're also doing change in y over change in x. We called this rise over run, and we chose any two dots we wanted to use, and we counted up and over, up and over, up and over. They did that for us, and they found out that constant rate of change is 11 2/10. All right, so the first thing we're going to do is look at their slopes. Then we're going to figure out their initial value. That would be their y-intercept. So it would make sense in this situation that at 0 minutes, neither robot has done anything yet. So they are both going to be linear functions. They are going to go through the data point 0, 0. So the data for the model GXN007, if I was going to compare them, had the greater constant rate of change. So it would complete more welding tasks per minute than the model T1000 robot. All right, so now we are at the try it, and just for fun and giggles, let's add a third robot. The welding robot of a third robot has an equation where T is the time in minutes and W represents the number of welding tasks. How does it compare to the other two? Well, let's go back and let's look through these again. We had our model T1000. That was the table. And if I was going to write the equation, y equals the slope, remember that was 10.4, plus the starting point, the y-intercept. All right, and then we had the model GNX007, that was our pretty graph. And if I was going to write the equation for that, y equals the slope, remember that was 11.2x, plus its starting point. And now we have this new guy, I don't even know what it is. We're going to call it the new guy. And we have his equation, y equals 10.8x. It's implied that it also has a plus 0 on the end. So let's figure out how it compares. Well, it looks like they all have a starting point of 0. So really the only thing I'm going to look at is the slope. The one that's going to make the most is this one. After that, the one that's going to make the next most welding tasks is number 2. And the robot that makes the least welding tasks is number 3. So if I was going to compare them, I would say the new guy is smack in the middle of the other 2. All right, example 1, we had 2 linear functions, and now we have a linear, remember that one's this guy over here, and a nonlinear, this guy over there. That one's nonlinear because it's not going to be a straight line. All right, so let's compare these two. A square with a side length s is shown. The table shows the relationship between the side length and perimeter as the side length increases. The graph shows the relationship between the side length and the area. How do the two relationships compare? All right, so this on the table, this relation is a function. It has a constant rate of change. So remember, we used to go this way, divide, 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 to see what our slope was. But today I told you that we can also go this way. Change in y over change in x. And it looks like we're increasing by 4 every time as our numerator. And we are increasing by 1 every time as our denominator. So if I wanted to be all sorts fancy, I could write that equation because it's linear. Y equals 4, that's my slope, 4 over 1 every time, plus, notice it starts at 0. All right, let's look at the next one. This relation is a function, but it doesn't have a constant rate of change. It is nonlinear, and because of that, I can't write an equation. So if I wanted to compare these, the only thing I can say is they are both functions. Every input has one and only one output. Beyond that, there's nothing else I can do because with a nonlinear function, I can't compare their slopes and I can't really compare their y-intercepts because it's not a straight line. All right, this is example number 3 on page 179. So we are looking at the properties of linear functions. And remember at the very beginning I told you there are 2 things we're going to focus on. We're going to focus on the slope. Your book will sometimes call it a rate of change. And we are going to concentrate on the y-intercept, which is the starting point. Now, should we be given an equation like this one, easy peasy, the slope is 2 and the y-intercept is -3. But we won't always be given an equation. Sometimes we've got to work for it. And so we are given, in this case, function b as a graph. Well, I can still do that. My slope is -1/2. They did the work for me. We would have counted rise over run, or in this case, fall over run. And the starting point is 7. So they did our work for us, and now we're just going to compare them. If I was going to compare the slopes, my 2 got a little crazy. If I was going to compare my slopes, well then function A is greater than function B. If I wanted to compare my y-intercepts, function B is greater than function A. All right, here is our try it on page 179, and we are going to compare the properties of these two linear functions. And remember the two properties we are comparing. We are comparing their slopes, also known as rate of change, and their y-intercept, or their starting point. All right, first we've got a table. And so we are always thinking about our change in y over our change in x. But it doesn't look at first glance like we are skip counting by the same amount. This change in y was 4.5. But then look here, I added 6. Oh my gosh, when I skip counted up here, I only added 3. And when I skip counted there, I added 4.5. That doesn't look like it's going to work yet. All right, so let's see here. Add 3, add 4, add 2, add 3. Let's just see what happens if we take our change in y over change in x. Let me do it again. Change in y over change in x. Let me try again. Oops. Change in y, change in x. And if you look, the last one is already done for us. If I were to divide all of those, I would get a slope of 1.5. Now, if you remember, we used to say that this was not a good slope, but that's when we were learning what slope was. We were counting rise over run, and so we needed a numerator and we needed a denominator. Now that we're more into equations and algebra, this will be okay. It'll be acceptable. All right, so if I wanted to start off with my equation for the table, y equals the slope times x, and I need a starting point. Now this one gets a little tricky. There's no 0, 0 in my table. So I am going to use something called point slope form. So in order to do that, I'm going to use any one of my ordered pairs. I'm going to use this one. And if you remember, y equals mx plus b. Well, the y is 1. The slope is 1.5. And the x is 2. I just took and I put 1 where the y sits and I put a 2 where the x sits. 1 equals 1.5 times 2 is 3. 3 plus what number is 1? Well, that number is -2. Now that is called point slope form, and we're going to do that lots and lots of times. So I don't want you to freak out if you did not follow that just now. It's fine. All right, so now it's time for us to compare our functions. So if I was going to compare the slopes, it looks like 2 is bigger than 1.5. So function 2 was bigger than function 1. If I was going to compare the y-intercepts, it looks like -2 is bigger than -4. So function 1 is bigger than function 2. All right, here is your key concept on page 180. When we are comparing functions, remember we are comparing two things. We are comparing the slope, otherwise known as rate of change, and the y-intercept, or the starting point. If you are given a table, You are looking for your change in y over your change in x to get your slope. And every time here it came out consistently, 3 over 1. And notice that went right there. And then they used something called point slope form to figure out their y-intercept. So what they did was they took this and they started plugging. The y, substituted in the y, and the x, substituted into the x. So now we have 4 equals 3 plus b, so b has to be 1. Point slope form is tricky. We are going to work on that lots and lots of times. But regardless, we have an equation y equals 3x plus 1. All right, if they give you the equation, super duper. And if they give you a graph, you are going to go ahead and count up and over. They did that for us. Y equals 2.5x plus the starting point of 10. When you are comparing these, you are just comparing slope, slope, slope. The one with the biggest slope is the first one. And then you are comparing y-intercept, 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 oops, y-intercept. The one with the biggest y-intercept is that one. All right, it is time for you to try the Do You Know number 4 and 5 on page 180. I want you to work through those. There is an answer key available for you to self-check.